Hello. Okay, today we're going to talk about phase changes. Last time we talked about if you add or remove heat from an object or a substance, it will raise in temperature or it will drop in temperature. Or if you put two substances or objects close to each other or and one is warmer than the other, you will get a heat transfer one to the other until their temperatures equalize. Okay, so that we have only dealt with one phase or one state of matter in those cases. Nothing changes its state of matter. Now we're going to transition and start talking about phase changes. What happens as far as heat transfer when something melts or something boils or something freezes. And that's where we're going to go from here. Now remember this PowerPoint is PDF on the classroom, so your notes should just be extra. Okay, so let's go with our review. At the end, we're going to do a very simple worksheet before we start moving into calculations. Okay, states of matter. We know solid, liquid, gas. Okay, we're not going to deal with plasma, but we are going to deal with the solid, liquid, gas. That's what we say are the states of matter. When there's a change between these states, they're called phase changes. So sometimes you'll have a solid, it will be referred to the solid phase or the liquid phase. And when when it moves from one to the other, those are called phase changes. Okay, they're caused by a change in heat or pressure. More often heat, but they can be caused by pressure. You can put enough pressure on gas to change it to a liquid, and then or from a liquid to a solid in some cases. But we're going to just deal with the heat part of it. So going on from there, we need to kind of differentiate a couple of terms. Heat and temperature, they're not the same thing. Heat and temperature, not the same thing. Heat is an energy, this is a measurement. Okay, so the temperature just measures the average kinetic energy of the particles in a substance. It's basically measuring how fast the particles are moving. It's measured in Celsius or Kelvin. Those are our two units of temperature. Okay, kinetic energy is directly related to the speed of the molecules. That's what we said, is it measures that kinetic energy. The faster the particles are moving, the higher the temperature. Kind of makes sense, hopefully. Heat. Heat is the measure of energy, and we talked about this in the last one in joules. Um, Heat and temperature are not the same thing, like we said. A cold Lake Superior has more heat energy than a pot of boiling water, but it's still cold. The temperature of it would be cold, but it's still, because of its amount of matter there, the heat energy is still, there's a lot of moving molecules is what that's saying. Lots and lots of moving molecules. So even though they're moving slower, there's lots of them. And a pot of boiling water, not as many molecules moving very quickly. Okay, so for this class, higher temperature though means more heat because we're going to be dealing with the same amount of matter. So heat always flows from a warmer object to a cooler object. We talked about that last time. Just like something can't roll uphill by itself, heat does not transfer from a cool object to a hot object unless you put energy in. Okay, so solids. We all know about solids. Solids are matter that the molecules are very tightly packed together. They have lots of bonds. They have high potential energy, which just means there's a lot of intermolecular forces. They're bonded together. They're nice and tight. The molecules are greatly affected by those intermolecular forces. They're nice and sturdy. The particles simply vibrate in place. They're very dense, and they're not easily compressed. So all this should be pretty much review. So here is our picture of our solid. Very organized, squared away. Our liquid gets a little more haphazard. Things are moving a little more freely. And gas are just there everywhere. They're bouncing off of each other, much more spread apart. Okay, so liquids. We just said they're not so tightly packed. They flow and can be poured, and they're just kind of mishmashed in there. They have a medium potential energy. They're still close enough to have those intermolecular forces, but it's lower, so they're able to move and not so much stick together. Now, Sometimes they do stick together pretty well and then you have surface tension, the ability of a liquid's molecules to stick together. This is where, and many of you have probably seen it, where you can float a paper clip on a glass of water, in a glass of water, and it just the surface tension, the water molecules hook together, they stick together like little magnets. It creates this nice surface tension, and then you can just lay that uh, paper clip on top and it'll just sit there nicely. Okay. Adhesion, on the other hand, is it sticks to other compounds. So that would be um, like when you are measuring water in a graduated cylinder and it's kind of coming up the sides of the cylinder, it's sticking to the sides of the cylinder. And then cohesion is when it sticks to itself, which is basically another way to say surface. It would relates to surface tension. Gases. They spread out as big as the container. So if you put gas in a room, it'll fill the room, regardless if there was no other gas in there. It spreads out, they move very high kinetic energy. Particles will move very quickly, but with the high kinetic energy, there's very little potential energy, if any. There's little effective intermolecular forces. They're not close enough to interact with each other very well. It's low density. It can be compressed, obviously, and very fluid, moving all of the time. But this all should be very much review. Okay, so a phase change. A phase change is when the substance changes states. Okay, it requires the input or the removal of energy or a change in pressure. Ice doesn't just melt. If it's kept at the same temperature, it'll stay ice. If you put it out in the sun, it starts to melt. But the sun is adding energy to that, and that's why the phase change occurs. Now, this is very important. During a phase change, the temperature does not change. The amount of energy does, but the temperature does not change. And we're going to talk about that. So what happens is all of that energy being put in is going towards breaking those intermolecular bonds and adding kinetic energy to the substance, but it's breaking all those bonds, and so all that's happening is if it's melting, all the energy is just going into changing it from a solid to a liquid. And we're going to talk about this little phase diagram in a little bit, and so hopefully it'll clear up a little more. But just know that if it's melting or boiling, the temperature is not changing. Okay, intermolecular forces. We talked about these briefly before. They're the interactions between particles that cause them to stick together. They're strongest in solids, weakest in gases. Strongest when the particles move slowly. During a phase change, these intermolecular forces, that's that IMF, are either weakened or strengthened. They're weakened if you're adding energy, they're strengthened if you're removing energy. Okay, so here is your different phase changes. You have evaporation from a liquid to a gas, condensation from a gas to a liquid, the freezing and melting you should know, the sublimation and depositions, solid to a gas sublimation, gas to a solid. Those we did introduce, you did see them at one point in 8th grade, but here's a review of those things and we'll talk about those in a little more detail. Sublimation, especially sublimation, you should know the other ones. A transformation of a substance to a gas, to a gas from a solid with no liquid. So it just goes straight from a solid to a gas. Dry ice does this. You set it out, dry ice doesn't turn into a liquid and then a gas. It just smokes. It just turns directly into a gas. And deposition is the opposite when a gas transforms into a solid without the transition through the liquid state. Frost forming on your windows. So if it's cold enough out, the water from the air will just freeze on objects. Okay, so here is what a phase change diagram looks like, and this one is for water, and we're going to use waters a lot. So let's talk about this a little bit. So if we see down here, we have ice. And 273, this is in Kelvin. Kelvin, this would be 0 degrees Celsius, but Kelvin is offset by 273 degrees because 0 Kelvin is when molecules stop moving theoretically. We've gotten close, we haven't got there. So Kelvin is based on absolute zero, and the freezing point of water is at 273 Kelvin, um, and the boiling point is at 373. The size of the Kelvin versus the Celsius measurements are the same. They just started a different zero is all. Okay, so here's water is in its solid phase, its ice phase. And you can see if you add heat to this, this is adding heat. You can see this at the bottom. Oh, you can't see it at the bottom. This, what we're doing from here to here, and it's on your PowerPoint. I didn't quite get it in this, in the screen shot here, but from here to here, we are adding heat. All the way across here, we're adding heat. So what happens here is we have a chunk of ice here, and we're adding heat, and we're heating that up basically to 0 degrees Celsius. Now, we're continuing to add heat here. This is where we're melting. The intermolecular forces are being weakened through here. The temperature does not change through this piece, but we are continuing to add heat. Then all of a sudden, all of it now is water. All of it is liquid water. Now we will heat it. We're continuing to add heat, continuing to add heat. Now all of a sudden we are now at the boiling. We are 100 degrees Celsius right here. We have a boiling pot right here. This is all boiling. And the temperature of this again does not change through that boiling water stage. If you have a thermometer at home, I I recommend you boil some water and just stick the thermometer in there and verify this. As it's boiling, even though the stove is still on and still adding heat, you are not changing temperature. So here we're just adding energy, turning all the water into steam. Once it is all steam, then as you add heat, you will increase the temperature of the steam. Okay, we're going to talk about these later. These are this heat of vaporization and heat of fusion. We're going to use these to determine how much energy this is. This span here, how much energy did we actually have to add to turn all this water into steam? And that is just determined by how many grams there are. See, the heat of vaporization is 540 calories per gram. So that means it takes 540 calories to turn each gram of water from a liquid to a gas. And so that's kind of where we're going to be going with this, but I wanted to get you familiar. This is melting point, this is boiling point. You can measure them straight across here and get you used to these diagrams, get you review on your phases, and then next week we will hit the actual calculations behind all of this. I believe that's our last slide for today. Nope, not quite. So where does all the energy go? We talked about this briefly. During a phase change, energy is added, but the temperature does not increase because that energy is going towards breaking up these intermolecular forces between the particles. Now, helpful info on this. Melting point and freezing points are the same thing. The only thing is if it's the melting point if you are going from a solid, if you're melting something going from a solid to a liquid. It's the freezing point if you are going from the liquid to the solid. So we just refer to those at the same temperature, but it depends on which direction you're going. Are you making it hotter, or are you cooling it off? Okay, so, and again, during a phase change, temperature does not change, but the amount of heat does. Okay, so we will take off from here next time. I will be loading that very simple worksheet so you can just kind of get your feet wet with this stuff. So until next time.